Hi, everyone. Welcome to our 19th session of the MedAI group exchange sessions. This week, we are very lucky to have Beliz Gunel from Stanford here with us to talk about her research on using untrained neural networks for MR reconstruction via both self-training and weak supervision. Beliz is a PhD student in the electrical engineering department here at Stanford and advised by John Pauly and works closely with Akshay Chowdhury and Shreyas Vasanwala. She's primarily interested in representation learning for medical imaging and natural language processing, as well as building data efficient methods that are robust to distribution shifts. So thanks so much, Beliz, for joining us today. And before we get started, do you have any preferences on how you'd like to take questions? Do you want us to interrupt you, or would you like it all in the end?
Oh yeah, I mean, happy to take questions throughout the presentation. Feel free to interrupt me. Yeah, meant to
Awesome.
be. Yeah.
Okay, so as always, let's try to make this session as interactive as possible. And without further ado, let me hand it over to Beliz.
Sounds great. Awesome. Yeah, thanks Nandita for inviting me. Happy to be here. Today, I'm really excited to talk about our work on self-training and weak supervision using untrained neural networks for MR image reconstruction problem. So first, I'll give a brief introduction to magnetic resonance imaging, or MR image reconstruction problem. It's an inverse problem in imaging. And then I'll share some of the key observations my collaborators and I have made and current challenges in this intersection for ML-based MR reconstruction pipelines. And then I'll discuss our work on weakly supervised image reconstruction using untrained neural networks. And then I'll revisit the key observations that we've made and give some pointers to the ongoing work. All right. So MRI is a pretty popular medical imaging modality that enables non-invasive visualization of soft tissue anatomy and physiology and giving, MDs great diagnostic information. However, if you've gotten MRI scan at all or really know anything about it, you know the data acquisition process is pretty time consuming, therefore giving really long scan times. So data acquisition is done in k-space, which you can think of as a frequency domain representation. And then there has been decades of research on this, on how to accelerate that using parallel imaging, compressed sensing, etc. So here you can see a representation of real image X and fully sampled k-space, obtaining all the samples in k-space, which gives result to this beautiful looking image. And by undersampling below Nyquist rate, we mean specifying an undersampling trajectory, and undersampled k-space looks like the following. And then if you just do nothing and take the Fourier transform of that inverse Fourier transform, you get this blurry image, which is zero filled. So
Can I ask a quick question in your previous slide?
Absolutely, yeah.
So this is all retrospective. So the real image is actually with the highest sampling rate that you have obtained from MR, and then you're trying to.
Yeah, that's right. So this is sort of just give a visualization on how these things work. This is not the regime that we necessarily operate at always. Fully sampled k-space is timely to obtain, and this is precisely why we're interested in data efficient methods actually.
Got it. Thank you.
So first, let me formally define what an inverse problem is. So you have measurements y, in this case in k-space, and you have a forward operator called A that gets these measurements from the underlying signal or image u, and then there's a noise generating process that's involved in this. And the reconstruction task is essentially estimating your underlying signal, from the given measurements y. And a lot of the tasks in imaging fit into this taxonomy, such as image deblurring, deconvolution, in painting, super resolution, CT reconstruction, MR reconstruction, which is the focus of this talk. And problem is inherently ill-posed, which means reconstructing a unique solution is either difficult or impossible without having some sort of prior knowledge about the signal itself. So Since 2017, there has been a lot of excitement in this field around using machine learning techniques for MR reconstruction problem, which led to like pretty stellar image quality and like fast inference time. So proposals like include variations of UNet using generative adversarial networks, etc. But the most successful ones are usually the ones that are motivated by the classical variation regularization approaches, so such as the one shown in the following. Essentially, they're given this equation. So I have this equation that I showed in the previous slide, and below there's like a minimization problem where D is the discrepancy between AU, the measurements, the true forward operator run through the underlying signal, and the Y. And then J is the regularization function, which usually incorporates some sort of domain knowledge you have about the signal, either it's sparse or like whatever. And a lot of the novelty generally came from that JU. So, so this is sort of like roughly the setup. And I think the key point here is like, the methods that sort of incorporate the domain knowledge usually have been tending to do better for this task.
Quick question, actually. So yeah. Is the distance D agreed upon by most people, or is that also subject to evaluation quality?
That's a great question, actually. So in the context of MR reconstruction, since we know the noise generating process is Gaussian, the discrepancy measure is pretty obvious for this inverse problem. So it's like L1, L2, like, it's pretty like well agreed upon.
I see. Got it. Okay.
But it's not true for all of the inverse problems, like where you don't have full knowledge of the process. Okay. So before I go into any of the methods or like conclusions or anything, I sort of want to point out like the key observations that we've made in this intersection. And sorry. Okay. So given the structure of this problem, we think the paired training data requirement, by paired I mean having access to fully sampled data as well as the undersampled data, is still pretty high for these ML-based models to get for acceptable performance in the clinic. And what do I mean by the structure of this problem? We exactly know what the forward model is, as I said to Nandita in like a couple minutes ago. The forward model is precisely undersampling times Fourier transform times coil sensitivity maps. So if we have this information already, we probably should be leveraging that. And of course, like there exist works that like started doing this by like simply, for example, integrating coil sensitivity maps alone is like a pretty strong prior to help constrain like the problem for the machine learning. But I mean, we also know a lot more, right? Like, and that's precisely how the traditional iterative approaches were designed in terms of regularization. We know like sparsity of the signal, like smoothness properties, like low-level image statistics. We have a lot of knowledge. And also, I mean, okay, I'm giving this talk to an AI community. One might say like, okay, why don't you just do data augmentation? If it's like a simple sample complexity problem, why don't we just do that? And my answer to that is like you can, and there have been a lot of people like who tried doing this, and it's still debatable whether or not it's like useful. But again, I'll go back to the notion of like we know exactly what the forward model is, so therefore we can simulate things better in the frequency domain and look at the image-based representations compared to like just blatantly doing image-based transformations, borrowing methods from computer vision. So I guess all in all, like I'm just saying, like the domain knowledge we have can be more effectively leveraged by directly getting encoded into the pipeline or within the network itself, which we think would lead to better data efficiency. And the second thing is I think it's like an ongoing theme for like machine learning these days is like these models also are very sensitive to distribution drifts, making them pretty dangerous to deploy in clinic. And to be more concrete about like what do I mean by distribution drifts in this scenario is like there are different vendors, right? There's GE, Siemens, etc. So there's scanner-induced drifts, which can be related to signal-to-noise ratio, resolution, coil failure, magnet drift, post-processing differences, and also related to anatomy change, patient-induced artifacts such as motion, which is very prevalent in all of the scans, off resonance, forward model change, which can include acceleration rate change, and also, remember I talked about like undersampling the case space, how you're undersampling the case space. So again, like I guess like a similar point, forward model and the nature of the noise generating process are known to us, so we can simulate these drifts and account for it during our model development and evaluation. So I think as a third point, I'm also making a point that's like true for a lot of the machine learning pipelines now, because measuring progress for this task is incredibly hard. And what do I mean by that? So first of all, best engineering practices around designing these machine learning based pipelines are not super well established yet, which makes it hard to compare like different approaches across different groups and like different companies, etc. And so we routinely use quantitative metrics called PSNR and SSIM, which some of you might be familiar with if you're working with image reconstruction. Of course, they tell us some stuff about like how well we're doing with the reconstruction, but they don't necessarily correlate that well with human perceived image quality or the clinical utility, which is in the end like what radiologists care about for making any diagnostic decision, which makes the model development cycle pretty long. So we think the model development cycle can be shortened by different evaluation methods that better reflect clinical utility. So, which I kind of already alluded to, is one of the primary motivation of this work is these supervised models, ML-based MR reconstruction models, still need, really large paired training data sets, like which requires access to fully sampled data. So we're interested in, can we reduce this data requirement without sacrificing the inference time? So like inference time is not usually spoken too much about in the context of ML, so like why am I talking about this? It's because like, you know, the conventional methods in MR reconstruction, such as compressed sensing, are based on iterative methods. So that means there's no training, so you're like purely doing inference, which means like during these iterations, you're spending a lot of time, so which is something you don't observe, of course, with a neural network, so because it instantly gives you the answer. So I'm having this table where like, okay, we have the state-of-the-art machine learning-based supervised methods where we need large data sets, but our inference time is short. We have iterative methods that are compressed sensing and untrained neural networks, which I'll speak more about, which is like something we're pretty excited about, that do not require any training data, which means you don't need any access to like fully sampled data. But then, just by the nature of being iterative, their inference time is really long. In an ideal world, we want short inference time and ideally no supervised data. So one of the things that we explored is like, there is this paradigm of like self-training that has shown really compelling performance boosts in computer vision and NLP. That's like a pretty simple idea, which some of you might not be familiar with it, so I'll just like go over pretty quickly. So essentially, if you have some labeled data, but you have like a lot more unlabeled data, which is exactly like the regime we want to be able to operate at, you train quote unquote like a teacher model with the labeled data you have, then you infer pseudo labels on your unlabeled data, and then train equal or larger student model with combined data that can or cannot be noise injected, and then you make that student your new teacher and you just like keep iterating. It seems like a pretty, you know, simple idea, but so this is from a paper from, I forget the exact name, this is the original one, the self-training with noisy student improves ImageNet classification. So they're showing like pretty impressive improvements in distribution case, and particularly for AC and P ImageNet, which are like the robustness data sets. So they're showing like pretty impressive improvements. So we were interested in, can we adapt that to MR reconstruction, particularly because like self-training have been shown effective in image to label cases, but like here we're operating at a image to image case for an inverse problem. Okay. And here I'm showing results for self-training in natural language. This is actually a work that I did with several Facebook collaborators. And here we were interested in looking into whether or not self-supervised pre-training and self-training capture the same information, or are they complementary? So is this benefit like solely coming from like doing some sort of self-supervision, or is it something that's like meaningful on top of like pre-training? And like I put the link, like it's an open source implementation, but the takeaway from this is like the answer was yes, you could do that. And also it gave like pretty impressive results for like especially few shot learning when you don't have much data, knowledge distillation, and also in like classical NLP classification benchmarks. Okay, so back to MR reconstruction. So I talked about unrolled neural networks a little bit, which are like motivated by the variation regularization approaches, as I said. So, and those are sort of like the state-of-the-art MR reconstruction methods for purely supervised now. So what we're proposing here is the following. Essentially, we're taking undersampled scans and fully sampled scans, so like a pretty limited pairs, train an unrolled neural network on them, use that as a teacher model to pseudo-label purely undersampled scans, which we have a lot, like, and we can always like get access to a bunch of undersampled scans, infer those pseudo pairs, which you can see like there's still like some aliasing artifacts, they're not perfect, but then combining these supervised pairs and weakly supervised noisy pairs, however you want to say that, pseudo pairs, and then train another student model, which is again an unrolled network. And then the goal is like, you know, you're leveraging a lot of the unsupervised data you have, but you're still getting like short inference time. So then the natural question is, okay, so if the interesting part lies in creating these like bunch of noisy paired data sets, can we have a stronger teacher model? Can we not rely on like this like unrolled network that's trained on like solely like some paired data? And there we were pretty interested in this new notion of like untrained neural networks that have shown pretty great promise in various inverse problems without requiring any training data. So there was this paper that came out in like 2018 called Deep Image Prior, which sort of started this like untrained neural network line of work that made like a pretty key observation. They essentially showed that structure of a convolutional generator, like simple like a decoder or like encoder decoder architecture, is sufficient to capture a good deal of low-level image statistics prior to any learning, like no training data. So what they're doing is essentially starting with random noise input Z, and F theta here is like the convolutional generator. And then you essentially try to fit to the noisy data. In a denoising problem, it's a noisy one. In our case, it's the undersample, which I'll come to. But they essentially show that like if you early stop, convolutional generator fits the signal faster than the noise, therefore acting as like an implicit denoiser, which is like a pretty interesting idea. But like in these in the figure that's shown on the right, you can clearly see that like, so there's an image, the noisy version of the image, shuffled, and then pure noise. And the convolutional generator that they're working with, which obviously the design of that is like something you need to like heuristically tune, is fitting signal a lot faster than the noise, just because it has a prior to represent natural images faster. So I think this shows the importance of like structure of the network resonating with structure of the data. So we found that pretty interesting and thought about applying that to like another inverse problem, which is the ConvDecoder approach. So here, your noisy image is the undersampled image. And again, you're doing like a similar thing, but now you have like the knowledge of the forward model. So we factored in the coil sensitivities, estimated with JSONs, and you also have some measurements now, like you know exactly what like some undersampled points can be. So at the end of each iteration, we enforce what MR community calls data consistency. Fourier transform of the output image to coincide with the original case space measurements. So this is like an example where you have a ground truth and a ConvDecoder output. It does like a pretty good job, and in several cases it performs better than compressed sensing. So it definitely can serve as an alternative to conventional sparsity-based image priors, such as compressed sensing. And
Quick question, actually. So this architecture, was it developed for this particular modality, or like how did they come up with this architecture for, because natural images and medical images probably have very different data statistics?
That's a great question. So that's exactly why I said like you need to like tune the architecture a little bit, but like surprisingly, even just like borrowing the decoder encoder layers that they have and like doing some experiments actually gave like pretty decent results, which is slightly surprising, but it's an empirical observation.
I see.
Yeah.
And when you say you have to tune it a little bit, like what will you tune it against? Like what is the...
Yeah, so these things, like as I said, like heavily depends on like how long you train for. Like that's like one parameter. So like how much noise you want to fit, I guess. And also like the depth and width of these networks, convolutional generators. And there is also some work like from Reinhard Heckel that compared like, you know, having just a decoder, both encoder and decoder, changing the structure of the convolutional generator itself. Because if you think about it, like essentially that F is serving as the regularization that doesn't fit the noise or like fit noise later.
I see. Okay.
So then we tried, okay, so we were looking for like a better teacher model. So why don't we just use ConvDecoder, these untrained neural, because it's going to be all in train time, like it's not going to affect our inference time. We can create these pseudopairs with this like ConvDecoder method that gives like a lot better results. And then we can leverage these like noisy training sets along with like the limited paired data sets that we have to train like a student unrolled neural network model. And the results were pretty good. So this is a pretty limited data setting, which means we're using only one supervised volume from like one patient and one weekly labeled volume during for 4x acceleration, so like 4 times undersampling of case space. So on the left side, you see the ground truth. Second column is model output, and third is like the input to the network, which is zero filled of like undersampled taken inverse Fourier transform, and error is between ground truth and model output. So if you look at the supervised baseline versus self-training versus ConvDecoder weak labeling, you can see ConvDecoder weak labeling does like a pretty good job in like reducing background noise and aliasing artifacts. Of course, I mean, this is not like super great quality because we're like operating at like a pretty low data regime, but it's, you know, pretty visible improvements over the supervised baseline. And, you know, we looked into changing the ratio of supervised to weakly labeled or noisy pseudopairs. These are some numerical results. Changing the number of supervised volumes and changing weakly labeled to supervised. And these were tested on Fast MRI, which is a benchmark created by Facebook, AI Research, and NYU. Okay, so...
sorry, can I ask a question here?
Yeah, for sure.
In your ConvDecoder, do you train this for each weakly labeled image?
Yeah, that's a great question. So yeah, it's per instance. Yeah.
I see.
Yeah.
And do you think that's important? So what happens if, or have you tried just training it once for all your 4 weekly labeled images?
Yeah, so that's a great question. I mean, sort of like it comes down to like, can you make this faster, or do you have to do like instance-based stuff? So not really. Like, you know, across different slices, you can still get pretty decent results, but across different volumes, like empirical observations tell us that like it seems like you have to redo it for every volume. But like I know there are some people who are like looking into this like direction as well, which is like in the realm of like how do we like batch do this thing. Yeah.
Thanks.
Right. So yeah, I mean, going back to the observations that we have, so using ConvDecoder to generate these pseudo labels at training time was only just like one example of like leveraging like the low level image statistics that we have. But obviously there are like a lot of ways to build in invariances more explicitly because we know exactly what's happening in case space. So one thing that's ongoing work with Harrisberg, Arjun Desai, and Batu Öztürkler is looking into building networks that are robust to motion at inference time and still like not losing performance in distribution. So this is a framework that they showed for different SNR cases for different noise levels. So we extended it to enforcing consistency between motion corrupted and not motion corrupted images. And so this is the framework. So blue here is the supervised, which is like your regular reconstruction pipeline, and red is the unsupervised one where you have undersampled case space. This is again like a similar scenario where you have only access to like few supervised volumes and like have a lot of unsupervised volumes. So artifact simulator in this case is like simulating motion because we know again like how we can simulate motion, at least like pretty simplistically in case space. So we can like teach the model to like map motion corrupted and not motion corrupted to the same thing. So that's like the consistency path. So this might remind you of like UDA, like work from Google on supervised data augmentation frameworks, which essentially showed, you know, doing supervised data augmentation consistency performs better than doing regular denoising based consistency. So this is sort of inspired by that, but like, again, we're trying to build pipelines that can do recon well, but also robust to motion. And we got pretty promising results. So here you can see like the supervised baseline model, our M2R model with light motion, and in the last row, motion to recon model with heavy motion. And again, errors show like the difference between ground truth and the reconstructed image. So if you look at the supervised baseline, the model output, the reconstructed image, looks pretty poor. And if you go to our like motion robust models, it gets like, especially in like the last row, it gets like to a pretty good performance compared to ground truth. And the second set of images sort of show that. And this is with like coherent motion, and that's exactly why these like, you see these replicas of the knee here. So we're pretty excited by this.
Sorry, what is light versus heavy in the previous slide?
Yeah, so that's a good question. So I didn't go too much into the details yet. But essentially, so the way we're simulating motion is by introducing phase errors in case space. And the amount of translation you're introducing is what we call, like we set a parameter for that. And like if it's small, then it's light motion. And if it's large, it's heavy motion.
I see. Okay. And here it's hard to say which one's better, but or is there some conclusion that you can draw here already?
I mean, first of all, it's like a lot better than the supervised baseline.
Yeah, that's definitely true, yeah.
And yeah, in a lot of these cases, I mean, in the error images, like I think it's like we can draw a conclusion that says like heavy ones performs better than the light ones, but in our quantitative results, which I'm not showing here, that seems to be the case usually. Yeah. So, okay. And to the last point that I have, measuring progress for this task is incredibly hard, as I said, and I was talking about like maybe we can come up with a novel evaluation method that can better reflect clinical utility. And we're actively working on a visual quality metric that's based on self-supervised models trained in domain for medical images. But also I talked about like, you know, engineering pipelines playing in a big role for this. So this is a work that's collaboration with Arjun Desai and Akshay Chowdhury and John Pauly, where we look into how much different parts of the machine learning pipeline affect the end result. So why do I say that, right? So I give an example on the top row from Fast MRI, which I mentioned as a joint effort between Facebook and NYU that gathered like a pretty big attraction to the field. But if you look at their test results and compare different models, you can see that like SSIM and PSNR changes are pretty negligible. It's like on the order of like third or fourth decimal points. And I mean, if you've ever like looked at the correspondence between change of the metrics versus the images themselves, like 0.001 SSIM improvement, it's nothing. And we're not Google Ads, so like we're not working with things that's like on that order of improvement. So then we were sort of interested in, okay, like even like which type of data we use, which type of acquisition we use, how we compute the metrics, how much like, so this is getting into MR specifics, but like generally how you gather the undersampled data is like you have like a centered region that's like fully sampled, which is called the calibration region, and then you sort of like from outer case space you start undersampling. And even the center fraction of like how much fully sampled region that you get makes like a huge impact on like the end result. So let's look at some of our preliminary results. So the first table that I'm showing here is simply how we're computing PSNR and SSIM. Are you computing based on the volume? Are you computing including the phase information, which usually people just take like the real part, like magnitude images? Do you compute based on the slice? So those are the differences. So PSNR scan metric here is including the complex information. PSNR scan magnitude is not including slices average of all slices, and etc. So you get the idea. So if you compare across the rows, PSNR slice is 33 versus PSNR scan magnitude is 37.81, which is like a huge difference. So imagine a case where like someone reported there, and this is not talked about often, by the way, like how you're doing these things. That's what I mean by not standardized. Some method that you're comparing to that you saw on archive computed with like PSNR scan magnitude, and you're doing PSNR slice, and you're like wondering like why it's not working. So this might be one of the reasons. The second table that I have here is related to the center fraction stuff that I was talking about. So center fraction just means what percentage of like the center part are you fully sampling when you're saying undersampled data. So, and this applies to across different anatomies, by the way, like knee and brain. So, and it's trained with like state-of-the-art reconstruction models. So changing the center fraction from 0.04 to 0.08 makes, like let's say like we're looking at 4x PSNR on knee, it goes from 33.5 to 34.6. So it makes like a huge difference. So I guess like the takeaway that I'm trying to like get here is like we should think about like how we're structuring these pipelines and like be careful about like the engineering decisions and like be transparent about them. So I talked about how maybe we should be looking into different evaluation methods to make the model development cycle a little shorter. So I also want to give a pointer to work with Phil Adamson, Jeffrey Dominich, Arjun Desai, and Akshay Chowdhury that we're looking into. And the reason why we're doing this is like there has been several works around showing PSNR and SSIM or like other metrics for these not correlating well with diagnostic quality for radiologists. And there has been some work in the computer vision world where large self-supervised model learning good image level representations. So like the question we're interested in, can we build a large self-supervised model that understand MR images well, so that when we're looking at the MR images at evaluation, it can say, this is a good image or this is a bad image. So here, again, I'm not going too much into details, but we're training like a large in-painting model where it's based on context prediction, where we're like sampling parts of the image, not showing to the network, masking it, and then have the network predict. And it sees like hundreds of volumes of MR images. And then now we are left with this like network that understands MR images pretty well. So we can use that network to extract features from the reconstruction models and then make some judgments. So here we see, so this is again from like the fast MRI, but you have like the fat suppressed and not fat suppressed volumes. And on the x-axis you see SSIM, and on the y-axis you see the perceptual loss that we're calculating based on our large self-supervised network. So first of all, there are like pretty clear outliers. So like the one that we're showing here is like, it has like a pretty nice SSIM, like larger than 0.9. It's considered pretty good. But then you look at the reconstructed image, which you can see on the right-hand side, and it's actually not that great. You see like clear aliasing artifacts. And we're saying that like obviously there are like few examples, we need to like go through like a radiologist evaluation for this, but our perceptual loss is picking up that it's actually not a good evaluation. So that's one thing.
Sorry, another question.
Yeah.
Is the perceptual loss difference in the feature space of your in-painting network?
Yeah, so it's difference between extracted features from the ground truth and the reconstructed image.
So you need the anyway for SSIM also you need the ground truth. So for both, so you take the ground truth and you take the reconstructed image, you pass them through your in-painting network.
So there's no in-painting going on after that, right? Like, so in-painting is just like an auxiliary task for like self-supervision. So you have like this like encoder now. So you get that, there's no in-painting, you just like extract features from your ground truth and reconstructed image.
But the encoder was used to seeing images with like patches missing out, right?
That's right. But like during that task, we're like randomly sampling different parts of the image. So like the hope is like it learns like an image level understanding, not like patch level.
I see. Okay. Yeah. So, but that is able to pick up these like these differences which humans would pick up, right?
Mm-hmm. Yeah.
That's interesting. Okay.
So I also have a quick question, but more about the plot. Like, what is the blue versus the orange exactly?
Oh yeah, so blue is the fat suppressed images and orange is non-fat suppressed images. So it's just like a contrast in MRI.
I see.
And, yeah. And since like non-fat suppressed images are usually brighter, which you can see here as well, like they usually tend to have higher SSIMs just arbitrarily. It doesn't really mean much. What is going on? Okay. And also we were sort of interested in, okay, like you can, how robust are these extracted features from the self-supervised network to just like shifting of the pixels? Like, so technically, like, you know, if you have an MR reconstruction, if it's like shifted by like 1 pixel, right, like it shouldn't affect the image quality. You should be like, yeah, okay, this looks good. But like SSIM actually decreases by quite a bit. Like if you just like look at this figure here, like y-axis is SSIM and perceptual loss on the right, and like the rolling amount, like how much you roll, like as you roll by a lot, like SSIM, like compared to the ground truth, decreases by quite a bit. I mean, this is of course expected because like, you know, like neural networks in retrospect rather, like should be picking up, like it shouldn't be affected by translation, but like this is like a good like sanity check that it actually doesn't. So like this could be useful for like differently registered reconstruction cases.
Is role a translation? What is role?
Yeah, just translation. So you can see like the shifted, like compare original minus shifted in like the bottom row. So it's just saving, yeah.
So 0.8 is 0.8 centimeters or something.
Yeah, yeah.
Okay.
Well, I mean, it's like based on some like NumPy thing, but like it's essentially like the amount of translation. Yeah. All right, thanks for listening. I want to thank all my collaborators that's involved with these projects, and yeah, I can take any questions.
Awesome. Thanks so much, Beliz. I guess we have like a fair amount of time for questions, so I'll open the floor up for questions now.
Awesome. Yeah, sounds good.
I can actually get started with the first one. So going back to your like the ConvDecoder for so was it the case that given a really good teacher model, did you need the ConvDecoder structure at all, or like were you able to see if that model by itself is able to perform like in a weak supervision way?
Yeah, that's a good question. So as you're increasing like sort of the supervised amount to train unrolled neural network on, unrolled neural networks get pretty good after like certain number of supervised volumes. So at that point, you don't really need like a different kind of teacher. So I guess the answer is no. Yeah, yeah.
Okay. Are there any other questions?
I'm interested in the perceptual loss thing. So can you explain in a bit more detail this, or I don't know if, because it's still in submission, so maybe you don't want to, but okay, as much as you would like. What is the procedure? How do you train this in painting thing? And then yeah.
Yeah, I think I'll defer the details like after like it's out. Yeah.
Yeah.
Oh, on that note, have a few radiologists actually looked at images and then evaluated, okay, the SSM, like the SSM corresponds to this value, but what does it mean for a radiologist? Like, has there been some study of that sort to actually get a feel for human quality metrics?
Yeah, so there has been some like just in conversation, but not in a formal way yet. Yeah, but it's gonna be coming up. Yeah.
I see. And is that evaluation typically like task dependent, or is there like a universal, okay, this is a good image versus not a good image?
Yeah, I think that's actually a great question. So that's still a debate in the community. Like, what does it mean, right? Like to have a good reconstruction. So I don't think there's a consolidated answer on that yet. And usually, how it's done is like you ask like pretty specific questions on like what you want to see. Like in this region, do you see blurring? Like overall. You know, like you give them like pretty like specific guidelines on like and it usually depends on like sort of the anatomy and like what type of sequence you're working with, etc. So like the expectations change also.
Oh, actually, this brings me back to another point that you had started out with. Like, I was very intrigued by the fact that there is a good sense of what constitutes a distribution shift in the case of MR, because most other domains, you don't have that knowledge really. And so anything out of the ordinary is going to be out of distribution. And so I was wondering if there is like, so I know that you did the pixel shift analysis in the end, but are there any other types of distribution shifts that you actually tried to see if they're robust against?
Yeah, so yeah, exactly. That's sort of exactly like the point I was trying to make actually. Like in a lot of these cases we know sort of like the source of like where this drift is coming from. I mean, for some of these it's not like as obvious, right? Like when I say like post-processing differences such as like frequency oversampling, this tends to be like dependent on like the scanner machine itself, and they don't like give you the trade secret, so like you're never gonna know kind of thing. But for certain things like motion, for example, like I showed an example here where like, you know, we're robust to motion. So that's like one example of distribution drifts. And so what this motion model is based on was actually an extension of what Arjun and Batu has worked on for different SNR changes, so like different noise levels. So that was another thing that we looked into. Because again, like we know exactly how to simulate noise in the MR case. Like it's just additive white Gaussian noise in space, so you can like simulate that and actually account for that. Like you don't really, but like for certain of these things, obviously, like it's harder to simulate. But like, and also like motion can happen in like a million different ways. Like it doesn't really need to be like, you know, some translation. Phase, etc. But like we know where to start. Like I guess like going back to my point about like we exactly know what the forward model. Okay, this is bad. We exactly know what the forward model is, so it's a bit easier to simulate.
Awesome. Are there any other questions? Okay, if not, thanks so much, Beliz. Let's give her a virtual applause. And we'll have the recorded video up by tonight on YouTube, so feel free to check it out. And yeah, Beliz will be like more than happy to hear from anybody else who has further points. And yeah, thanks again, Beliz, and hope to see you all next week.
Awesome, thank you so much.
Thank you. Bye-bye.